Hi, welcome to es301 Engineering Analysis. This is chapter 19 on Fourier approximation. So here are the learning goals. At the end of this, you'll know what a Fourier approximation or curve fit is and when it's a more efficient technique. You'll recognize how an arbitrary signal can be broken down into component sinusoids. You'll know how to determine the component coefficients. You'll understand the relationship between the time and frequency domains, and you'll be able to convert a periodic, non-sinusoidal signal from the time to the frequency domain. So first, let's just give a little background about why we would care about Fourier approximation. Well, what that little sample was about 5 seconds from Leper Messiah by Metallica. And so let me explain why I played that and what this has to do with Fourier approximations. So here I'm showing just a little small sub-second sample from that song that we just heard. And if you look at it, this is all the data that contains within that song as it's stored in a digital format. But one of the things about this, if you look at it, is that you see we've got kind of a periodic signal that looks kind of like this. But on top of that, there's also some high-frequency signals on top. Now, what we often want to do when we have this much data is we'd like to go ahead and compress it. And that's what happens with formats such as MP3, where you take an original audio signal and you convert it into a smaller data file that is not as large as the original data file. The original data file, these tend to be sampled at thousands of times per second. And so you've actually got a whole lot of data points. And so what we would like to do is be able to find some way that we can turn this large amount of data into some little small amount of data. And in fact, a typical compression can be anywhere from 10 to 70%, essentially depends on the type of audio signal. And so what we're going to be looking at is how this is done. And so the second plot that I just showed, there's a red dotted line on top of the blue line that has about a 30% reduction in the amount of data. But if we kind of blow up and look at what it looks like, if you look, that red line looks like it's just on the blue line. And so in terms of fidelity of this song, you probably wouldn't be able to tell the difference if I was playing the red line or the blue line. And we're going to look in this video at kind of the fundamentals to how this type of compression occurs. All right, so that brings us to this concept of a Fourier approximation. And this is related to curve fitting. So this fits in with the last couple chapters where we've talked about where we have a bunch of data points, and what we're trying to do is fit some type of curve to it. Now, if we look at this curve right over here, we have, I think it's about 14 points in here. And if we were to go ahead and curve fit this, we could go ahead and put some sort of polynomial in there, right? Maybe like an a0 plus an a1x plus an a2x squared, etc. If we kind of look at this, we realize that this actually, we've got sort of this sinusoidal look to it. And in fact, if we wanted to break it down into a couple components, it sort of looks like this red line, where I've got just a regular sine curve, and then this purple line, because I've got kind of a general trend up to it. And in fact, what that purple line is, if I just look at it at that point, is kind of a lower frequency signal on top of the red line. Now, I've also got this offset. If this over here would be 0, I've got a little bit of offset. So maybe I really should say it's 3 signals, 3 sinusoidal signals. I've got the offset, which would be this green function, and then I've got a component that is the red one at a higher frequency, and then I have the purple one at a low frequency. So if I was to combine these 3 curves right over here, I might end up with something that looks pretty close to that. And so what I would need to do is just go ahead and specify what the amplitude is of each one of these signals and what the frequency is of the signals. And actually what we'll realize is that if this data was regularly spaced, often we don't need to concern what the distance is between each data point. If it's a regularity, we just save what the single delta t was. We can do a similar thing when we have our frequencies, is we'll go ahead and just look at it at some fundamental frequency, and then the second fundamental frequency, and the third fundamental frequency, and we'll just have coefficient values for each one of them, and then all we need to do is store what the amplitude is of each one of the signals. And if we just didn't want to include one of them, we would just set that amplitude value to 0. So that's kind of the crux of how we're going to be doing this. Okay, let's look a little bit more in kind of details of how we do this. So here's this signal that I showed before, and what we'd like to do is determine what would be a good sinusoidal representation of it. Well, what we could do is we could say, well, it looks like it might have an offset. That would be like this a0 value, which is effectively a0 times the cosine of 0, for example. And then we've got our fundamental frequency, which is omega naught here. And omega naught, just so you know, is 2 pi over the period, which the book uses the notation t. So I've got my fundamental frequency times time, and then I might have a sine component. And so sine is considered an odd function, cosine is considered an even function. If I look at it around 0, cosine is even because it looks like this. It looks the same on the right and the left. And since sine is a mirror image, it's considered odd. So cosine is considered an even function, and sine is considered an odd function. And often I want to have both even and odd components, or I need to have a phase shift of each one of them. So we'll look at kind of doing it both ways. Okay, so here's what I want to do. I want to fit it to this function here, and right now I'll just look at one fundamental frequency at sines and cosines. And so how would I find out, essentially determine what these coefficients are, A0, A1, and B1? If we think back to when we did curve fitting before, what we did is we went ahead and found out what the square error was, and so that's what this value of S sub r is. So we're just taking the actual value we have and then effectively our model fit, and then what we're going to do is we're going to be taking the derivatives, dsr, dA naught, set that equal to 0, same thing with A1 and A2, and then solve those series of equations to determine what those coefficients are. If you do it, this is what the values are, and it's effectively over the sample that I have. I'm going to sum up all my y values and divide it by the number of samples I have for A naught. And then I'm going to do a similar thing for A1 and A2, or A1 and B1, but now I'm going to be at each one of the data points that I'm looking at, I'm going to be multiplying y times the cosine of omega t, so it depends on what time that occurs at. That's all going to give me a value for A1, and all of that goes into this value of A1 that I will then multiply by cosine omega t. So note that you evaluate the omega t to get the value of A, and then you're actually going to put it into your function yet again. Okay, well, the previous example we looked at was we just looked at one single frequency, one fundamental frequency. But what if we wanted to go ahead and have several frequencies in there? Because what we look at, for example, this curve here doesn't look like it's just one frequency. I'm probably going to have to add kind of a large frequency and a lower frequency as well. And so I need to determine how many of these that I want to go ahead and include. And in theory, you don't know how many different frequencies you might need. And so what this kind of leads to is the idea of a continuous Fourier series, where now I'm going to replace my summation with an integral. And so if I go ahead and do that with an integral, some of the details are in the textbook, but the actual derivation isn't as important as the net result, is now I've got these coefficient values A and B, and the book uses lowercase notation just to indicate this is for a continuous Fourier series. And this is 2 over t, where t is the period. And then I'm going to integrate my function, that's effectively the value of y on the previous slide, and then cosine k omega t, and k is going to be taking values like 1, 2, 3, all the way up to, well, you could effectively do it into infinity. And the more frequencies I include, the better curve fit that I'm going to have. All right. Now, another thing is you might wonder, well, what is the period? How often do I curve? How do I determine how long to put it? Well, normally Fourier series is done for functions that kind of have some type of periodicity to it, like this, where it's fairly easy to go ahead and say, oh, here's my repeat section. And so this value right there would be my period of capital T. Right? And so, well, that's kind of the crux of what we want to do. All right, so let's go ahead and look at an example here of how we're going to go ahead and determine a continuous Fourier series for it. And this is, you want to kind of look at this example carefully because it's really easy to kind of lose a sign here and there. So I'll try to kind of go slowly through it. So this is the function that we want to get a Fourier representation to. And we realize there's a periodicity to it, but it's clearly not a sine or a cosine function. But we're going to need to add a bunch of components together. And so it's just a value of 1, that's for a certain period of time, and then -1 for another period of time. And so I can look at my period of value of t, right? And it can go from like maybe minus t halves to t halves, or you could look at it from going from 0 to t. Any of those is a repeat section. Right, so what we want to do is we want to go ahead and integrate our function. So here's our function f of t. It's right in there. Well, you realize it's 1 sometimes, and then it's -1 other times. And in fact, what I realize is that the value of this is going to be 1 right in this upper area. So it's going to be from minus t over 4 to t over 4. And then it's -1. So again, there's f of t right there. And it's f of t from t over 4 to 3t over 4. So I'm just kind of breaking my integral up into 2 parts because at some point it is 1, and then at another point it is -1. And so now I need to go ahead and perform those integrations. And so the integral of cosine is a sine, and then I've got to include this coefficient value right out here. So it's going to be t over 2 pi k, because that's what this term is right there. And so now I went ahead and performed my integration, and now I'm going to need to evaluate. And the first one is going from minus t fourths to a positive t fourths, and the other one is going from t fourths to 3t fourths. Right? And so I'm going to go ahead and evaluate, and that's what the values I'm going to be putting in for my value t there. Now, look, I can go ahead and I've got this 2 out here. I can go ahead and cancel that, and my t over there as well. So I can go ahead and cancel those terms out, and now I just got a 1 over pi k there, just to kind of simplify it. All right. So now what I'm doing is I'm evaluating my value of sine. And so, for example, if I do that at minus t fourths, so if I look over here, I'm doing this at minus t fourths, and the sine of minus t fourths, if I put that in here, what I realize is going to be the value of 1. And then if I do it at minus t fourths, it's going to be minus 1. I subtract the two sides. 1 minus a negative 1. This is where I say you need to be kind of careful and, to make sure you don't lose a sign. And now I'm going to be adding my second evaluation. But now I'm doing it from 3t fourths to t fourths, and actually my values here now are going to be minus 1 subtracting a positive 1. And when I did my integration, I still have this minus 1 term right over here, because this is the value from f of t. Okay, so that's where this minus 1 comes in. You get a lot of minuses in here. Now, if you go ahead and do this, you've got 1 minus minus 1, so it's going to be a positive 1. This over here is going to be a negative 1 minus 1, but you've got a negative here, so you end up with a value of 4. Right? Now this is if my value of k, for example, was equal to 1. And so what happens if, for example, k is equal to 2? Let's look at and perform our integration if k is equal to 2. Okay. So again, we're doing this from minus t fourths to t fourths, but now I've got k is equal to 2, so this value of k is twice as much. And now actually my sine values are all going to be at values of pi and 2 pi, etc. So I've got 0 minus 0 there and 0 here. So this one over here is now going to be evaluated to 0. So I get a different integration value if I have k1 or k2. Well, let's keep going. Let's look at k is equal to 3. And so if I do that, now I'm up at 3/4 t quarters. So effectively what I've done is I've shifted what was the second term now becomes the first term. First term becomes the second term. And so the sign of this flips, and now I've got minus 4 over k pi. And if I go over to k is equal to 4, I'm going to realize it's equal to 0, and then it begins to repeat. So effectively, I can determine what my coefficient values are, right? And so these are the values of a of k. I can determine what those are. This is for values of k equal to, for example, 1, not 2 or 3 or 4, but 5, not 6, 7, or 8, but 9, and etc., etc. When k is equal to an even value, it's going to be equal to 0. And then when k is equal to 3, not 5, but 7, not 9, 11, etc., it's going to have this negative value. And now you can go ahead and include as many terms as you want. K equal 1, 2, 3, 4, 5. You probably would just go ahead and skip all the even values because they're always equal to 0. And as I do that, I'm going to get a better and better approximation to what this square wave looks like. All right, so the next thing I want to talk about is converting from the time domain to the frequency domain. So let's go ahead and look at this signal I show over on the right. And if you look at it, just kind of, I can obviously see some periodicity to it, but it's probably kind of a mixture of a few different sines because I've got sort of a long sine function there and one of a little higher frequency as well. And in fact, what that is a plot of is this function here, where I've got cosine of 2t, 4t, and 5t. And then I've got some different amplitude values, 0.2, 0.3, and 0.4. So this is just a plot. So this is f of t as a function of t. Okay? Well, if I wanted to, I could go ahead and represent this a little differently. As I could say, okay, well, here are my coefficient values, the 0.2, 0.3, and 0.1. And that occurs at a value of 2t's, 4t's, and 5t's. And so this right over here is my amplitude value. So what I'm doing is effectively I'm fitting this to some constant, to use notation in the book. It's C1 times the cosine of t, and then there would be some sort of phase shift each time. Now if I take this same signal that I just plotted, and then if I go ahead and look at it this way, it looks like an entirely different signal, but it turns out this is the same one, except that I have shifted one of the curves forward by pi halves. And everything else didn't change. So it looks like a very, very different signal. There's only one small difference, which is this phase shift there. So there's two pieces of information I could go ahead and convert this to. This amplitude values, and then also I would want to know my phase shift values. So that this is labeled wrong. This should be 0.5 right there up at the top. And so here at my frequency of 2, right, I've got a phase shift of pi halves. At a frequency of 4, I have a phase shift of 0, and same thing at 5. And so now if you look at it, you've got 3 data points, those 3 values of my amplitude, these 3 values of my phase shift. And that would be another way to go ahead and represent this signal in those 6 values. And so what I've done now is I've converted from what is considered the time domain, these plots over here on the right, to what is the frequency domain, which is the plots over on the left. So first I want to go ahead and just kind of look at the book example of this, and then we'll do our own example of this decomposition. So this is back to the function that we looked at before, where we went ahead and had those values of k equals 1, and then the evens, they were zeros, etc. And if you look at, this is the breakdown of the various components. So this black line up at the top, this is the first primary component. This is a cosine function because it is an even function. And so this is the lowest fundamental frequency, so it's cosine of omega t. Now the next one up is going to be 0, and then the next value down, which is 3, and all the even values were equal to 0. So now I've got cosine of 3 omega t. That's the blue curve, and if I add the blue curve to the black curve above, I get this new black curve. And now you realize we're starting to approach that sort of blocky look that we had before, which is what our aim is to do. Now if we go ahead and go up to our next value, which is our value of 5, this is the next blue curve. Now remember, on the odd values, the values of k switched each time, which means my coefficient values switched each time. Let's come back and look at this. The fundamental frequency, we have a positive amplitude there. Then we had a negative amplitude and then a positive amplitude of the components. That was that switching of the values of k. So if I want to go ahead and look at this in the frequency domain, this is what the two plots would look like. This is my coefficient values of the amplitude. At the fundamental frequency, I had a value amplitude of 4 over pi. And then when I went down, I ended up with 3/4 of that value. So now I went up there with this at a value of 3. And the next one I go down, I've got a fifth of that value right there, and it continues down. So this right over here would be, and I could keep going, and they would keep getting smaller and smaller because the value of k was in the denominator. Now if I look at my phase shift, my fundamental frequency, this top plot, had no phase shift at all. Phase shift being where is the maximum of that curve, because these are cosine functions. So there's no phase shift to the cosine function, so my amplitude or my phase shift would be 0. And the next one over, I've got this completely out of phase, so it's like a phase shift of pi. You could also think of it as a phase shift of minus pi, either way. And so this is why that's over there at pi. The next one had a phase shift of 0, and then I had a phase shift of pi, etc. And then that would just keep going on as I went ahead and included higher and higher frequencies, higher and higher values of k. Right. So let's go ahead and do our own example here and try to kind of construct what this would look like in general. So here's the function that I'm going to do. It's kind of this whole sawtooth looking pattern. So kind of maybe I can think of some little connections like this. But more or less it goes down and then it's back up to 1 and then it repeats and goes back down. And what I would like to do is kind of try to guess or try to figure out, not really guess, what the amplitude and phase shift spectrums of this might look like. Okay? So remember what I'm fitting this to is C1 times the cosine of t plus some phase shift. So over here, these are my amplitudes. These are my values of C1. And so let's kind of think of how some sinusoidal functions added together might end up approaching this sawtooth. And so what you realize is, well, first of all, this is an odd function. And so it's really going to need to be a phase shifted cosine, or what would be a cosine function. And it goes down. So maybe it would be, for example, a sine function, like primary frequency might look like that. And the period of the first primary frequency is the same as the period of the black line. So if I look at this, what this would be more or less something with a negative amplitude. And so my first primary one is going to have some sort of negative value. It might be down to 1 or whatever, depending on how large the black values are. Now, if I look, I need to now kind of go ahead and adjust this curve that I did, which means I need to go ahead and bring these values up a little bit. So my next one, which would be the higher frequency, I'm probably going to want to go ahead and put out of phase. And so this one's going to have a positive amplitude, but a little bit smaller. So now my plot might look like that. And so I could imagine that as I go up to each one of those fundamental frequencies, they're going to be switching in the amplitude and getting a little bit smaller. So qualitatively, it would look like that. If you did the integration of this exact curve, you could determine exactly these values. But we can kind of qualitatively get an idea of what it looks like. Now, the next thing we want to do is we want to go ahead and determine what the phase shift would be. Oops, sorry. And so let's go ahead and look what our phase shift would be. This would be our values of phi. And so again, remember, these are fitted to cosines, but I have over here is of a sine function. So I need to go ahead and shift that. And so I need to shift that up, for example, at about pi halves. Right? So go ahead and go from the sine to the cosine. So this one might be phase shifted up at pi halves. And then the next one, I'm going to go ahead and phase shift down negative pi halves. And the next one up at a positive pi halves. And the next one at negative pi halves. So I keep moving them back and forth. So qualitatively, this would be what my phase shift would look like. This is what my amplitude would look like. You can kind of get an idea of what the general function is without doing the integration. If you go ahead and perform the whole integration, like our very first example, you can determine exactly what these particular values are. Okay, let's go ahead and review what we talked about in this video. First, we saw many signals are sinusoidal, and they can be fit to a series of cosine and sine functions quite efficiently. We saw that the best fit series is determined similar to a least squares by minimizing the square error. A continuous Fourier series accounts for all frequencies up to infinity, and then that results in an integration. We saw that arbitrary function coefficients are determined by evaluating the integration for the desired function we are attempting to fit. And we saw that either the time or the frequency domain can be used to contain the information within the signal.